This tutorial is about implementing 2D wave equation PDE, which is primarily, again, a second derivative with respect to time, but then also the second derivative with respect to x and y, and the c is the speed of propagation. Now if we discretize this, we have a 2D mesh with I and j indices, and if we let delta x equal to delta y, we get this difference equation that would be very easy to implement. And you can see how this delta ij becomes 4 times delta ij because there's a contribution from both x-axis and y-axis. So this can be implemented, and just the way we did it in the 1D case, if all the boundary values are 0, then it becomes a reflecting boundary. So when the wave reaches the end, it will be reflected back. But we can also implement merge boundary condition just like we did in the x direction. We can exactly create y direction boundaries, and these are the discretized versions of those boundary conditions. So just take your 1D equation, 1D code, and implement the second dimension into it. So ly is 10, dy is equal to dx. We also get the number of elements in the y direction, and then we create the line space in the y direction. The total number of seconds is 10 in this case, and we have the 2D arrays to hold the current value, then n-1 value, and then +1 values of the wave, the variable. And in this case, I'm setting up the CFL condition to 0.5. The 1D case was easy. One will work, but in 2D case, one will not work. We're letting the propagation speed to be 1, and so that gives us dt value that we need to increment the time loop. There are no initial conditions because we're going to introduce a source in this case, delta t squared times f. Here's the reflecting boundary condition first. All the boundary values are 0, and then we save the current variables, and then we have the source here at the middle 50-50. It's again a sine wave with an amplitude of 20 times dt squared. And here is the double nested for loop going from 2 to nx minus 1 and 2 to ny minus 1. So all the inner nodes are computed, and beside the updating of the indices, make sure that you add this second part that is coming from y-axis into this for loop as well. And here I have visualized it in two ways. One is by just displaying the image of the value of the wave variable, which in this case is more of a deflection, and then I'm also plotting it as a mesh so you can see it in 3D. This command c-axis fixes the color axis, so the color will range from -0.02 to 0.02 depending upon what your amplitude is. That here this could be a different value, but you'll have to play with it. So again, going back from here, you have the domain, the values of the variables, the reflecting boundary conditions, the main loop to update the values, and then visualization. So let's run this. So the top one is the image, the bottom one is the mesh, and you can see there's a propagating wave from the middle, which is 50-50. That's where the sine wave is serving as a source, and you can see that the wave is propagating towards the boundary. Now once it reaches the boundary, you will see that it will get reflected back from all directions, and then as it is reflecting, it's also interfering with the incoming wave. So you have all this very interesting pattern that is forming, which is basically the interference pattern of all these waves adding and subtracting at different angles. So in order to remove this reflecting pattern, all we have to do is just make sure that we have some absorbing boundary condition. So let's go back here and remove the reflecting boundary condition and add the absorbing boundary condition that I have already coded up. Again, this is implementation coming from the MERS boundary condition that I have given in the manual. So let's run this again and see how does the boundary condition works in this case. Again, same wave from the same source propagating in 2 dimensions. And now mind you that you can in a similar way introduce the 3rd dimension, but it becomes a little tricky to display a 3-dimensional wave. But you know how to do those kind of things. So here the wave is approaching the boundary, and you will see that it will not get reflected. There's still a little bit reflection because there is no perfect boundary in 2D case, but overall you can see that the wave is pretty well absorbed into this boundary, and you might see some corner effects appearing. You can see that if you're running it for longer duration, you will see that some reflection is happening, but it's so small that it's very difficult to detect it. So hopefully this will give you intuition of how to run, how to implement a 2D wave PDE in MATLAB, and what are some of the things that you have to take care of as you are implementing it. Something that you may have noticed that this was a very slow code, but you can display every maybe 0.5 seconds to improve the speed of this display.